Okay. So today we're going to talk about reinforcement learning for simulated autonomous vehicles and their controls. I'm Sammy Wood.
And I'm Justin Cliver. So the problem we're trying to solve is learning a control policy for autonomous vehicles. Specifically, we're looking at using reinforcement learning, which uses trial and error to learn the model of a control system in this scenario. And we want to look at the current state of the vehicle and score how good they are. And that will be our reward function for our algorithms. Specifically, we want to make sure the car is on the road and in the middle, preferably facing the right direction and not veering off course. The states and the actions will eventually become associated with positive and negative rewards as the algorithm learns. And then theoretically, these algorithms will develop good driving techniques. So, our motivation for doing this is that current self driving cars don't have the level of intelligence needed to handle many different environments, such as like dirt roads or cities versus rural areas. The we believe that reinforcement learning is a very quick and efficient way to explore many possibilities and adapt to situations that the algorithm hasn't seen before. Here's some of the related work that we're drawing from. A few of these papers reference different algorithms we possibly could use and we'll present later. And then we also were inspired by some previous research into driving the donkey car, which you will see in our simulator later. And we will take a look at three different algorithms. DDQN, which is a discrete action space algorithm that uses a convolutional neural network to associate pictures with actions. We'll look at soft actor critic, which is an actor critic based reinforcement learning algorithm. And then we'll look at PPO, which is a proximal policy optimizer that will try to estimate the correct policy to take when driving. Our assessment criteria will be based on the best reward of each algorithm and in the evaluation stage on a new environment that it hasn't seen before, how easy it is to use and implement and train, and then finally the amount of time it takes to train.
So the first algorithm we're going to present today is DDQN. The main idea behind DDQN is to map images to actions. So we can see examples here. If the car is veering off to the left, uh, an image of that would correspond to the action of correcting right. If we're going in a direction that seems good, we would want to continue doing that. And if we're veering off to the right, we would want to correct left. So, like Justin said, we're dealing with a discrete action space. To simplify the problem, set the throttle to a low and slow value, partially because of training and computational speed. We bend the steering into 15 different angles. Um, so each one of those angles will correspond to turning or staying straight. The architecture of the network is shown here. So we start out with a 120 by 160 RGB input from a camera. That gets resized to 32 by 32 after doing some image augmentation. And then 16 frames are stacked. On my computer, that corresponds to about half a second of video. Um, and then through the convolutional process, we map out eventually to 15 different states, those 15 states being the steering angles. So some of the things that we tried for image augmentation, um, detecting the yellow and white and superimposing them on the original image. Uh, Sobel edge detection, just looking for the edges. Trying to detect the road using a canny edge detector. And finally, the one that we settled on, uh, just looking for the center line, the yellow line shown in the picture on the left. So our final selection was just to look for the center line, the yellow line shown. This shows the process that we went through for our image augmentation. The original image is converted to just look for yellow. So you can see where the white is the yellow line. Then we apply a blur and resize the image, mostly just to speed up the process of convolution. Some other things that we considered were how to set the reward function. So some things that we looked at were the inverse cross-track error, looking just at the change in cross-track error, the heading error, and then a combination of both heading and cross-track error. So there's some issues with using just cross-track error or heading error alone. These pictures give a demonstration. So on the top left, you see a good position. However, if you just think about cross-track error, being in the middle of the road, shown on the bottom, even though you're heading the wrong way, would have a very similar reward function. So in that case, you might not be learning quite the best policy. Similarly, on the right, the two positions of the car have the same reward if you only consider heading. So in both cases, the car is heading in the correct direction, but in the bottom right, the car is offset. So the solution is obviously we had to consider both. So the results of the DDQN, it worked fairly well. It took between 50 and 100 episodes to train, and it can complete the track without crashing, but it has to drive slowly.
Moving on to Soft Actor Critic, one of the advantages is that it has a continuous action space, so it has a higher potential for fine movements, unlike DDQN. It's considered to be the state of the art in machine learning or in reinforcement learning applications, and it can be done on the training can be done on a CPU rather than a GPU because its network architecture is relatively simple. However, it's not designed to handle images because it can be trained on a CPU, and its action space makes training difficult. It can learn many different possibilities, whereas DDQN is more constrained, which can lead to simpler results. So in order to make Soft Actor Critic work, we have to augment the input. And the way we do that is through two main ways. We have a custom implementation of Soft Actor Critic that we made from scratch. And we also had to implement a variational autoencoder. And what this does is it takes the image, encodes it into a vector of features, and then that vector of features goes to Soft Actor Critic. But at the same time, it has to be trained to make that vector of features the same every time it receives the same image. So in the training phase of Soft Actor Critic, we're also training this autoencoder that encodes an image and then decodes it and compares the output of the encode and the decode, or it compares the input image to the decoded image. And that can make training very unstable, and it makes results kind of weird if you don't tune it correctly. And with any autoencoder, it is kind of difficult to tune it in conjunction with an advanced algorithm like Soft Actor Critic. Additionally, we implemented a smooth steering angle action. So instead of taking the regular action from Soft Actor Critic, which could send the wheels turning from negative 15 degrees to 15 degrees, we implement a smoothing function to make it slower turning so it doesn't just wiggle around on the track. And the throttle was also limited to between 0 and 25% because we wanted to leverage some of the continuous action space that Soft Actor Critic offers, but we don't want to necessarily just drive at one speed the whole time either. And we do want to drive slow. And as a result, we found that Soft Actor Critic struggled to learn the turns, and that the VAE and Soft Actor Critic, training them simultaneously, just was very unstable and difficult to implement. The continuous action space made it a difficult training environment for Soft Actor Critic to actually learn the course, and it doesn't actually complete the course as well as DDQN. Overall, we found that DDQN has the best performance and was really easy to implement, and that Soft Actor Critic has a ton of potential, but a lot of things can go wrong if it's not tuned perfectly. Reinforcement learning can be used to effectively control the donkey car as we found in our simulations, and further work just needs to be done to make sure that Soft Actor Critic can be tuned effectively to meet the performance goals that we wanted.